In this video, we're focusing on the addition rule, which is the rule that we use to find the probability that one event happens or that another event happens. For example, if I roll a pair of six-sided dice, what's the probability that I get at least one 1 or an even sum when we add the dice faces together? That's an example where we're asking the probability that one event or the other event occurs when I roll a pair of dice. Sometimes this kind of probability is disguised as at least probability, because we could ask something like, what is the probability that we get at least one heads when we flip a coin 2 times? Well, really, at least one heads is the probability that we get either one head or 2 heads. So it's still the probability of one event or the other occurring, and in that case, we would use the addition rule. In fact, let's go ahead and take a look at that example, the probability of getting at least one heads. First of all, if we're flipping a coin 2 times, we can think about all of the possible outcomes. So if we flip a coin 2 times in a row, we can either get heads heads, we can get heads tails, we can get tails heads, or we can get tails tails. So there are only 4 possibilities when we flip a coin 2 times. Now, sometimes we might be tempted to do something like this. We're looking for the probability that we get at least one heads, so we might say, okay, well, I have to get either heads on the first flip, or I have to get heads on the second flip. One of those things has to occur if I'm going to get at least one heads. So I could say, what's the probability that I get heads on the first flip? I look at all my options here and I say, well, in both of these examples, I get heads on the first flip. So the probability of heads on the first flip, which maybe we'll call the probability of H sub 1, meaning heads on the first flip, is going to be 2 out of 4, or 1/2. And then I could say, well, what's the probability that I get heads on the second flip? Well, this outcome and this outcome both meet that criteria, so I could say the probability that I get heads on the second flip is, again, 2 out of 4, or 1/2. And then I might say something like, the probability that one of these occurs, probability that I either get heads on the first flip or heads on the second flip, is 1/2 plus 1/2 equals 1, or 100%. But I know that's not true. Saying the probability that I get heads on the first flip or heads on the second flip, or at least one heads, is not 100% because, of course, I know that I could get tails tails. I could get tails on both flips. So if I can get tails on both flips, of course, that means that the probability of getting at least one heads can't possibly be 100%. So where did we go wrong here? Well, the problem is that we've double counted an option. We have an overlapping value in our probabilities that we're counting in both, and we can't do that. For the probability of getting heads on the first flip, we counted heads heads and heads tails. And then for the probability of getting heads on the second flip, we counted heads heads again and tails heads. The fact that we're double counting heads heads is what's throwing us off. One way that we can illustrate this overlap is with a Venn diagram. So we could draw a Venn diagram like this one, and we could say that one circle represents getting heads on the first flip, and that the other circle represents getting heads on the second flip. Now, with Venn diagrams, I always like to start with the overlapping area between the circles, the area in the middle, which is all of the outcomes that meet both criteria. So for the number in the middle here, we're looking for all outcomes where we get heads on the first flip and we get heads on the second flip. Well, we know that that occurs here at heads heads, so there's one outcome where that occurs, so we could put a 1 in the middle. Then over here on the left, we're looking for all of the outcomes where we get a heads on the first flip, but not heads on the second flip. Well, that happens here. We got heads on the first flip, but not on the second flip. There's one outcome, so we put a 1 over there. Over here, we're saying how many outcomes occur where we get heads on the second flip, but not heads on the first flip. There's one of those, so we put a 1 here. And then outside both circles, how many outcomes are possible where we don't get heads on the first flip or on the second flip? In other words, we don't get heads either time. Well, that's this option here, tails, tails, so there's a 1 out here as well. In the Venn diagram, then, we're illustrating the overlapping value with whatever is in this overlapping area of the Venn diagram. So whatever's in the middle are the number of overlapping outcomes. What we want to do is subtract that out. So if we go back to this idea of the probability of getting heads on the first flip or heads on the second flip, which is really the probability of getting at least 1 heads, we could write it out this way instead. So we could say the probability of getting heads on the first flip, we know that there are 2 outcomes that meet that criteria. We saw those up here with the yellow check marks, or we could look in our heads on the first flip circle and see that there are 2 outcomes inside that circle. So there are 2 outcomes that meet that criteria. Or the probability that we get heads on the second flip, we know that there are 2 outcomes that meet that criteria. We saw those with the blue check marks here, or we can see that there are 2 outcomes inside the heads on the second flip circle. So again, we add in those outcomes. But then here's how we correct. We subtract out the overlapping value. So there's 1 outcome that is overlapping between those 2. This one that we double counted here with both check marks. So we have to subtract out that. There are 4 possible outcomes total. So we subtract out 1, the overlapping value, divided by the total number of possible outcomes. So we subtract out 1/4. When we do that, we get 2 plus 2 is 4, minus 1 is 3. We get 3/4 or 75%, meaning a 75% probability that we get at least 1 heads. And we know that that's correct because if we look here at our 4 possible outcomes, 3 of those will satisfy our criteria of getting at least 1 heads. We get at least 1 heads in this outcome, at least 1 heads in this outcome, and at least 1 heads in this outcome. But we do not get at least 1 heads when we get tails, tails. So 3 out of our 4 possible outcomes satisfy the at least 1 heads, so the probability is 75%. What we need to realize is that in order to get there, we had to subtract out this overlapping value. And that's really where we get to the addition rule. So the addition rule tells us that the probability of A or B happening, so event A happening or event B happening, is equal to the probability that event A happens plus the probability that event B happens minus the probability that A and B both happen. So this comes right from the formula we already built without knowing the actual formula, which was, we said here, this is the probability of event A happening, getting heads on the first flip. Add to that the probability of event B happening, that we get heads on the second flip, but then subtract out the overlapping value where we get heads on both flips. We're double counting it, so we want to make sure we subtract it out so that we don't get that double counting. If we generalize that into a formula, what we get is the addition rule. This is the addition rule here, also called the sum rule, and this is the formula that we use. Now, it's interesting to say that if the events are mutually exclusive, which means that there is no overlapping value between the events, if there's no overlapping value, then the probability that A and B both happen is 0. So for mutually exclusive events, which we also call, by the way, disjoint events, then P of A and B equals 0. And so if we plug that into our addition rule, this term here becomes 0, and we say the probability of A or B is simply the probability of A plus the probability of B, because we would just have minus 0 here at the end, and that would have no effect. And this should make sense to us, because if we calculate, for example, rolling a 6-sided die, and we want to know the probability of rolling a 2 or a 3, well, if this is a regular 6-sided die, all 6 faces are equally likely to appear, so the probability of rolling any value on that die is 1/6. So the probability that we roll a 2 or a 3 would be the probability of rolling a 2, so the probability of rolling a 2 plus the probability of rolling a 3. The probability of rolling a 2 is 1/6. The probability of rolling a 3 is also 1/6. So the probability then is 2/6 or 1/3. In an example like that one, the probability of rolling a 2 and a 3 is 0 because we're talking about rolling a dice only one time. And if I roll the die once, it's impossible for me to get a 2 and a 3 on that one roll. They can't happen at the same time. I can only get one result at a time. So the probability of getting a 2 and a 3 on one roll is going to be 0, which is why those are mutually exclusive or disjoint events. We don't have this probability of A and B term. It disappears as 0. And then we can simply add the probability of each of those events together without having to subtract out anything for overlapping events. But when we do have overlapping events, like we did in this first example, we have to pay attention to this probability of A and B term and make sure to subtract out those overlapping outcomes. Now let's go ahead and move this portion down because I want to look at another version of the addition rule. So this exact same addition rule can also be written as the probability of A and then this symbol B is equal to the probability of A plus the probability of B minus the probability of A, this symbol, and then B. So what are these? Well, this symbol that looks like a U is called union. And it basically means or, right? We said the probability of A or B. Well, that's the same thing as A union B. It means that either A happens or that B happens. This symbol is called intersection, and it basically means and, the probability that A and B happen, or the probability of A intersection B. You'll very often see the addition rule written this way with the union and intersection notation instead of the or and notation. They mean exactly the same thing. It's just two different ways of expressing the same rule. We can also calculate this kind of probability where we use the addition rule and we look at the probability that one event or the other happens when we have a two-way data table. So in this table, we have males and females across the top, and then their favorite sport or their preferred sport down the left-hand side. So as an example, there are 22 males who prefer football. There are 8 females who prefer basketball. You can see here there are 60 total males in the survey, 40 total females in the survey for 100 people total, and there are 41 people total who prefer some sport other than football or basketball. So their favorite sport is something other than football or basketball. So we've got a lot of data in this chart, and we can do lots of addition rule probability with a chart like this one. So for example, we could ask something maybe like, what is the probability that someone in this survey is male or prefers football? So their favorite sport is football. That's the probability we want to figure out. Well, we could break this down. So we could basically say that event A is the person being male. Event B is the person preferring football. Then if we're using our addition rule formula, we know that we're going to need to find the probability of A and the probability of B, P of A and P of B. So what are those? Well, the probability that event A occurs, the probability that the person is male, let's see. Well, if we sum up our entire male column, we have 60 males total in the survey, and there are 100 people in the survey overall. So if 60 of our 100 people are male, then the probability that somebody in the survey is male is going to be 60 over 100, or if I reduce this fraction to lowest terms, 3/5. So there's a 3 out of 5 chance that somebody in our survey is male. What's the probability that somebody in our survey prefers football? Football's their favorite sport. Well, I can again look at the total, and I can say there are 38 people who prefer football over any other sport, and 100 people total in our survey. So the probability that somebody's favorite sport is football is 38 over 100. Or if I reduce that to lowest terms, 19 over 50. But remember, according to the addition rule here, I have to subtract out the intersection of A and B, the probability that A and B both occur at the same time. So if I say A intersection B equals male intersection football, well, where in my table does male and football occur at the same time? That's here in this top left cell where I have 22. These are the number of people that are both male and prefer football. So this is the intersection of male and football. So I want to say the probability that A and B both occur, so A intersection B, will be equal to 22 of the people in our survey divided by all of the people in our survey, 100. And if I reduce that to lowest terms, I get 11 over 50. Then I can use the addition rule and say the probability that the person is male, event A, or prefers football, event B, so the probability of A union B, is equal to the probability that the person is male, which we said was 3/5, plus the probability that the person prefers football, which was 19 over 50, minus the probability that both occur, they are male and prefer football, which is 11 over 50. Now, if I want to find a common denominator, I want to multiply this first fraction by 10 over 10 so that I get 50 in the denominator. So 3 times 10 is 30, 5 times 10 is 50. So now I have 30 over 50 plus 19 over 50 minus 11 over 50. So I did that so I would have a common denominator, and now I can combine all three fractions. So 30 plus 19 is 49. 49 minus 11 is 38. So my probability is 38 over 50, or if I reduce that to lowest terms, 19 over 25. If I convert that to a decimal, I get 0.76 or 76%. So there's a 76% chance that someone in my study is either male or prefers football. So 76 out of my 100 total participants are either going to be male or prefer football. They're going to meet one of those criteria. Now, we did a lot of math here in order to apply the addition rule. But the cool thing is that we can actually just see this visually in our table. So here's what I mean. The probability that the person is male is given here in this column. We know there are 60 people who are male in our survey. The probability that someone prefers football, we know is 38 out of 100. 38 of our participants prefer football. And we know that the overlap of male and football is given here as 22. So really all we need to do is grab those three numbers and say that the probability of male or football is equal to the probability that they are male plus the probability that they prefer football minus the overlapping portion where they are male and prefer football, and then we just divide that by the total number of participants, 100, which is really all we did here. And we can see that we get that same value. 60 plus 38 is 98. 98 minus 22 is 76. So we get 76 over 100, or 76%. Alternatively, although this is really doing the same thing, we could take the entire male column and the entire football row, but only include the male and football intersection once. So for example, if we only took here all of the males, and then we want to make sure we don't double count the 22, so we won't box that again, but we also need to include everyone who likes football, so we're missing this box here, we need to grab that as well. In that case, we're just saying that these are all of the people we want, we just want to make sure we don't double count 22. So if we add all of those up, 22 plus 13 plus 25 plus 16, we get 22 plus 13 is 35. 35 plus 25 is 60. 60 plus 16 is 76. So we get 76 people out of the total of 100 participants, or again, 76%. So I'm just showing you all of these different ways to reinforce the idea that all we're really looking at is all of the people who meet one criteria or the other, and making sure not to double count the people who meet both criteria.